everyone. Today I want to talk about one of my personal favorite pieces of mathematics, which is the Euler characteristic. It's defined by the Greek letter chi, and it's the vertices minus the edges plus the faces of a particular shape. Let's look at finding this Euler characteristic for some different three-dimensional shapes and see what happens. So I'm going to start with my tetrahedron, which is just a pyramid. As far as vertices, we have 1 on the top and 3 along the bottom for a total of 4 vertices. For edges, I have 3 going down the sides and 3 along the bottom, so that's a total of 6 edges. And for my faces, I have 3 along the sides and 1 along the bottom for a total of 4 faces. If I add that information to my chart, I get 4 minus 6 plus 4 is equal to an Euler characteristic of 2 for the tetrahedron. Next, let's look at my triangular prism. For vertices, I have 3 along one side, 3 along the other for a total of 6 vertices. For edges, I have 3 on one side, 3 on the other, and 9 across for a total of 9 edges. And for faces, I have 1 on each side, that's 2, plus the 3 along the center gives me a total of 5 faces. If I add that information in my chart, we have 6 minus 9 plus 5 is equal to 2. So once again, we get 2. This is starting to look suspicious, but let's look at a little bit more. Next up, let's look at the cube. The cube has a total of 4 vertices along the top and 4 along the bottom for 8 vertices. For edges, we have 4 along the top, 4 along the bottom, and 4 down the sides. That gives me a total of 12 vertices. For faces, I have 1 on the top, 1 on the bottom, and 4 along the sides for a total of 6 faces. And we can see 8 minus 12 plus 6 is once again equal to 2. So this pattern is starting to look a little bit suspicious. Let's do a couple more shapes just to verify. Next, I'm going to look at the octahedron. As far as vertices, we have 1 along the top, 1 on the bottom, and 4 along the edges for a total of 6 vertices. For edges, there are 4 on the top, 4 on the bottom, and 4 around the sides for a total of 12 edges. And for faces, I have 1, 2, 3, 4 on the top, and 4 on the bottom for a total of 8 faces. Adding this to the table, we can once again see 6 minus 12 plus 8 is equal to 2. Next up, let's do something really big, the icosahedron, also known as the D20. I don't want to sit here and count all of the edges and all of the vertices. That seems a little bit cumbersome, but let's see if we can find shortcuts for this. Each of the faces is a triangle. Each triangle has a total of 3 vertices. The fact that this is called a D20 is because it has 20 faces. So 20 triangles would have a total of 60 vertices. However, each vertex has a total of 5 triangles around it. So 60 divided by 5 gives me a total of 12 vertices. For edges, each triangle has 3 edges. Once again, 20 triangles, that would give me 60 edges, but each edge is shared by 2 triangles, so 60 divided by 2 gives me a total of 30 edges. Adding this information to the table, we once again get an Euler characteristic of 2. So this is starting to look very, very suspicious. And let's see if we might be able to break this. Next up, let's look at the sphere. And while I don't have a perfect sphere, we can simulate this with a balloon. And spheres don't have vertices or edges, or really faces. But I can draw points and lines on a sphere in order to simulate this. The simplest way we can do that is to put a single vertex, and then connect that vertex with a single edge. Now I can see I have 1 vertex, 1 edge, and 2 faces. Adding this to my table gives me once again an Euler characteristic of 2. And we don't have to do anything that simple. It actually turns out that no matter where you put your vertices, you can put as many or as few, as long as it's greater than or equal to 1, vertices on here, and connect them to form some polygon faces, then the Euler characteristic is going to be 2. And so before I look at breaking this pattern a little bit closer, I want to examine that thing I just said about the sphere, that it doesn't matter how many vertices or edges I put on the sphere, the Euler characteristic will always be 2. Let's assume I've put some points on the sphere and connected them with some vertices, so I have some kind of decomposition. I want to look at how I might be able to change that decomposition. What can I add to that decomposition? And I'm starting with a pentagon, but we can really start with whatever shape we might happen to have on our sphere, even if it's just the single dot and vertex. There are only so many things we can do. One of the things I can do is add a vertex along an edge. So I've added a vertex, but I've also added an edge. I haven't changed the number of faces any, but when I added my vertex, I went from one edge to now 2. Since I added a vertex and added an edge, I changed my Euler characteristic by including an extra vertex and an extra edge. I can distribute that negative sign to make this v plus 1 minus e minus 1 plus f, and then my 1 minus 1 cancel, and I end up with v minus e plus f. So adding in this extra vertex did not affect the Euler characteristic. If it was 2 before, it's still 2. Now let's assume we have our decomposition that we want to look at. We know that we can put a vertex along any edge and it will not change it. But what if we just connect two vertices that weren't previously connected? Something like this here. I haven't changed the number of vertices. I did add in an extra edge, but I now have 2 faces instead of 1. So while I added an edge, I also changed the number of faces by 1. So I added in an extra edge and an extra face. Once I distribute my negative sign, I have vertices minus edges minus 1 plus faces plus 1. And once again, my negative 1 and 1 cancel out, and I end up with the same Euler characteristic I started with. So connecting two vertices that were previously unconnected don't actually affect the Euler characteristic. There is one more thing I could do to my decomposition. I could add a vertex somewhere that's not already on a line. This does violate the idea that this does have to be a polygon, since I can't have a point in the middle, so I will have to connect some edges in order to make it a polygon. And it turns out I need to connect at least 2. So let's start with just connecting 2 edges. In this case, I've added a vertex, I've added 2 edges, and I took what was 1 face and now made it 2 faces. So I added a vertex, 2 edges, and 1 face. So as I add in 1 vertex, 2 edges, and 1 face, I'll distribute my negative sign. That gives me v plus 1 minus e minus 2 is equal to f plus 1, which is vertices minus edges plus faces. So this doesn't change the Euler characteristic at all either. And any other thing that we do to our decomposition is going to be some combination of these. We either have to add vertices or add edges. We talked about the only way to add edges between 2 vertices, and the only place we can put a vertex is along an edge, which was our first case, or not along an edge, which is this case. So it turns out it's always going to be the same. And that brings me back to my original decomposition. I had a decomposition where it was 2, and now I showed that it won't change no matter what else we do, so it has to always be equal to 2. Next up, let's look at my torus, which is just the mathematical name for a donut. This is kind of a square one, but turns out that actually doesn't matter. If I count up my vertices, we have 1, 2, 3, 4 along the top, 4 along the bottom, and 4 along the inside, which makes a total of 12 vertices. For my edges, I have the 4 along the outside, the 4 pointing in, so that gives me 8 along the top, plus 8 along the bottom gives me 16. I have these inside, so that gets me up to 20, and then the 4 along the sides gets me up to 24 edges. For my faces, I have 4 along the top, 4 along the bottom, and 4 along the sides, which gives me a total of 12 faces. This time, when I try to find my Euler characteristic, I end up with 12 minus 24 plus 12, which is 0. So it's no longer 2. We broke it. So what exactly happened here? Why wasn't it 2 like the rest? And the answer is the Euler characteristic is detecting the whole. If I look at my other shapes like this cube, it was a solid shape, whereas the torus has a hole in the middle of it. And the Euler characteristic is one of the ways we have of detecting these holes in our objects. It turns out if we actually have a donut with 2 holes, the Euler characteristic is different again. This time it's -2. So the Euler characteristic, like I said, one of the many ways we have to detect the number of holes inside of a shape or an object. So Euler's formula says that for any convex polyhedra, the Euler characteristic will be 2. So what does that mean, convex polyhedra? Polyhedra essentially just means a 3D shape, so we need a 3-dimensional shape. And convex refers to the type of shape. If I look at my octahedron, what convex tells us, if I pick any point on this octahedron and any other point, and I try to connect those points, I will go through the shape. I'll be completely inside of the shape at all points. And no matter what 2 points you pick, you will always be completely inside or on the boundary of this particular shape. That makes it convex. On the other hand, we have this shape here. This one's not convex, because if I were to pick this point here and this one here, if I were to connect them, I see that I'm not actually inside the shape at all. I'm on top of the shape. I'm outside of the shape. So this one would not be convex. And the Euler formula tells me if my polyhedra is convex, the Euler characteristic will always be 2. So let's look at why that is. So I want to start with any polyhedra, and I'm going to use the cube, but only because that's a little bit easier for me to draw. This actually works no matter what shape we start with. You'll notice as I walk through this, none of this is dependent on the actual shapes that I draw. And what we're going to do is we're going to take our shape and we're going to remove one side of it. If we're thinking about a cube, we can think about a box without a lid. So it's the exact same shape, we just lost one of our faces. When I remove one face, I actually now need to show that vertices minus edges plus faces, this Euler characteristic, is equal to 1. This is because whenever I take that missing face that I removed and add it back in, I'll be adding in an extra face. So I'll be adding 1 to this value. I want it to be equal to 2, so for now I need it to be equal to 1 so that I can add the face in to get it to 2. Now that I have the idea, I'm going to take my shape that's missing a face and I'm going to flatten it. I'm essentially going to flatten my box. I'm going to think about a net of the shape on a piece of paper. And I want to look at that. One of the really nice features of topology is that we get to pretend like everything's made out of a rubber or a Play-Doh. Things can stretch and shrink as much as we need them to. We just can't rip new holes or glue things together. So when I flatten out my box without a lid, the edges, the corners don't actually separate, they just spread out. So it looks like this, where I have the bottom of the box and the 4 sides that are still connected. They no longer look like squares, but like I said, that's okay because we can think about it as made of rubber. We just stretch different parts of the square. The next thing I'm going to do is I'm going to take my shape. If you start with something that's not a cube, it doesn't look exactly like this, but that's okay. Whatever shape you happen to have. Any shape any polygon here that is not a triangle, make it a triangle. So I'm going to add in these edges, and I already showed that that's perfectly fine. Adding edge connecting to vertices that were not connected doesn't actually change the Euler characteristic. So far we're doing great. We haven't changed anything. Now that I have this in triangles, I'm going to find triangles with one border edge, things that touch the border with exactly one edge. And then I'm going to remove that edge. This one here we can see doesn't border at all. It's completely surrounded by other polygons. But this one here does. It does have a bordering edge. So I want to remove that edge. And it turns out that's not going to affect anything. I didn't remove any vertices. I did remove an edge, but in the process, I've also removed a face, since there was a face with this triangle that's no longer there. So I removed an edge and a face. Distributing makes this v minus e plus 1 plus f minus 1, which is vertices minus edges plus faces. I didn't change the Euler characteristic. And I'm going to keep doing this. One by one, I'm going to remove these edges for any triangle that has exactly one border until I can't anymore. Now I can see I only have two types of triangles. Those that have two border edges and those that have none. Next up, I'm going to find triangles with two border edges, and I'm going to remove both of the edges. So this triangle here, I can remove both of the edges, and we'll notice I removed a vertex, I removed two edges, and I removed a face. Since there was a triangle here, that's no longer here. So I removed one vertex, two edges, and one face. Distributing, I have v minus 1 minus e plus 2 plus f minus 1, or v minus e plus f. So once again, I didn't change the Euler characteristic. And I'm going to keep going. One by one, I'm going to slowly find each of these triangles and erase them. At this point, I have two triangles. One of them, we'll start with the top one. This one has two border edges. And now this final one has three. So I can't do anything with it just yet. But I can find its Euler characteristic. We have three vertices, three edges, and one face. This gives us 3 minus 3 plus 1, which is 1, which is exactly what we needed to show. Once we attach our missing face, we get back to 2. We add in our extra face. So as long as we started with a convex polyhedra, we will get an Euler characteristic equal to 2.